In 1989, if you wanted to build an unlicensed game for the Game Boy, Nintendo left you with an impossible choice. Design your cartridge so the console refused to start, or put Nintendo's trademark into your code, and hand them the grounds for a federal lawsuit. This wasn't laid out in a licensing contract, and it wasn't settled in a boardroom. It was hard-coded into 256 bytes of memory right on the main processor. By building a hardware check that forced cartridges to feed the system a registered trademark, Nintendo turned federal trademark law into a built-in security lock. And that set off one of the strangest legal battles in video game history. Almost everyone who owned a Game Boy ran into this at least once. You put a game in, flicked the power switch, and instead of the clean Nintendo logo rolling down the screen, you got a solid black bar, or a scrambled mess of glitchy pixels. The screen froze, there was no startup chime, and the game wouldn't load. The fix everyone tried was pure playground habit. Pull the cartridge out, blow into the plastic slot, and jam it back in. Most of the time, the real issue was simple dirt and wear. The Game Boy's 32-pin connector used small spring-loaded metal fingers to touch the gold contacts on the cartridge board. After years of use, dirt, skin oils, and slightly bent pins created bad connections. That corrupted the electrical signals traveling between the cartridge and the console. When a dirty pin froze the system, nothing had actually broken inside the machine. The Game Boy was doing exactly what it was programmed to do. Inside the custom processor, a tiny startup program ran two separate steps with the cartridge data. First, the chip read 48 bytes of graphics from the cartridge and loaded them into video memory to build the scrolling logo. Once that logo finished rolling down and the startup chime played, the processor ran a quiet check. It read the logo data off the cartridge a second time, comparing it byte by byte against a permanent copy stored inside the chip. If a dirty pin corrupted even one single bit, the screen showed whatever broken image made it through, and the security check failed. The processor immediately looped back onto itself, locking the console up before the game could ever start. To see why Nintendo built a check like this into a portable console running on 4 AA batteries, you have to look at how they ran their business in the late 80s. On the NES, Nintendo locked down game publishing with a dedicated security chip called the 10NES. The console had one 4-bit microcontroller acting as a lock, and every official cartridge had another acting as a key. The two chips ran a constant, private handshake back and forth. If the key was missing, or if the chips lost sync, the console reset itself once every second, causing the red power light to blink. When Gunpei Yokoi and his team at Nintendo R&D 1 started working on the Game Boy, they followed a different philosophy: build simple, reliable hardware using cheap, proven parts. Leaving out a second security chip saved space on the board, kept cartridge manufacturing costs down, and helped save battery life. Nintendo wanted the Game Boy to sell for $89.95 and run for around 15 hours on 4 AA batteries, all while keeping unauthorized publishers off the system. Instead of adding an expensive security chip, Nintendo's engineers used trademark law as the gatekeeper. Nintendo's patent family for this system goes back to a Japanese filing in January 1989. The US version followed in 1990 and was granted in 1992 as patent 5134,391. The patent describes reading character data, like a company trademark, from a cartridge, drawing it on a screen, checking it against an internal copy, and stopping the game if the two don't match. The patent spells out the legal trap directly. It notes that if an unauthorized cartridge copied the data to pass the check, that cartridge would be using the manufacturer's trademark without permission. Under Section 111.14 of the U.S. Lanham Act, using someone else's registered trademark in a way that confuses customers is civil trademark infringement. Copyright lawsuits often ran into defenses like fair use or clean room reverse engineering. But trademark claims gave Nintendo a different kind of deterrent. If an unlicensed publisher put Nintendo's trademark inside their game ROM just to bypass the hardware lock, Nintendo could take them to court for trademark infringement. If you left the logo out, the Game Boy wouldn't boot. If you put it in, you were copying Nintendo's trademark. The entire startup sequence was handled by just 256 bytes of machine code, stored in a tiny mask ROM inside the processor. The processor itself was a custom Sharp chip built around an 8-bit core known today as the Sharp SM83. It pulled together instructions and register layouts from both the Intel 8080 and the Zilog Z80, running at just over 4 MHz. When you turned the power on, the processor started reading code at address 0. Its first step was setting the stack pointer to FFFE, right at the top of internal memory. From there, it cleared out the 8 kilobytes of video memory between addresses 8000 and 9FFF, wiping the canvas clean so no visual junk flashed on the screen. Next, it went after the cartridge header. The 48 bytes stored between addresses 0104 and 0133 weren't raw image tiles. To save space, the logo was packed into a compressed bitmap. The boot code unpacked that data with a quick routine. It took each byte, split it into 2 halves, and expanded each piece into 2 bytes of pixel data. That enlarged the graphic by 2 times in both directions, built the full tile set, and dropped it into video memory starting at address 8010. Then it set up the screen registers. It loaded the background palette for high contrast and set the vertical scroll register so the logo started just off the top edge of the visible screen. As the display drew each frame, the code moved the scroll value down step by step, gliding the logo down until it settled right in the center of the glass. That's when the 2-tone chime played, and only after the chime finished did the real security check begin. At address 00E0, the processor set up its registers. It pointed register pair HL to address 0104 on the cartridge, and register pair DE to address 00A8, where the boot ROM kept its own copy of the logo. The chip stepped through a comparison loop, reading 1 byte from the cartridge and 1 from internal memory, checking all 48 bytes one by one. If even a single byte didn't match, the code executed a 2-byte jump instruction that pointed right back to itself, freezing the handheld in place. If the logo matched, the bootloader ran one last test, the header checksum. The routine loaded an accumulator with a starting value of hexadecimal 19, decimal 25. Then it added up every byte of game metadata between addresses 0134 and 014D, which included the game's title, publisher code, and memory configuration. The final 8-bit total had to equal 0. If it didn't, the machine jumped straight into the same freeze loop. Calculating that checksum was easy for any programmer, but it made sure the cartridge header hadn't been corrupted while the system was powering up. For years, people assumed that iconic startup chime was the Game Boy saying everything was verified and ready to go. The assembly code shows the exact opposite. The chime plays before the security checks even start. The sound wasn't a recorded audio file. The bootloader synthesized it live using Sound Channel 1, a hardware pulse wave generator built right into the Sharp chip. The code set up the audio by writing directly to hardware registers. It wrote hexadecimal 80 to register NR11, giving the sound wave a 50% duty cycle. Then it set the volume and decay rate in register NR12. To kick off the first note, it wrote hexadecimal 83 to register NR13 and 87 to register NR14. That started a low-frequency square wave. The code didn't use a separate timer to hold the tone. Instead, it tied the sound directly into the screen drawing loop. As the logo settled into place, The code held that first tone, wrote hexadecimal C1 to shift the frequency higher, and triggered the bright second note. Once that tone faded, the processor finally moved to address 00E0 to run the logo comparison and header checksum. The chime sounded like a green light, but the gates hadn't actually opened yet. Once the checks passed, the bootloader had to deal with a tricky architectural problem. It had to completely disappear. The 256-byte boot ROM sat at addresses 0000 through 00FF. But standard Game Boy games kept their own startup code, interrupt handlers, and vectors in those exact same lower addresses, with the game's main entry point waiting at address 0100. If the boot ROM stayed mapped to the bus, the system would crash the moment the game tried to run. Nintendo solved this with a single control register at memory address F50. Near the end of the boot code, the processor loaded the value 1 into its accumulator. At address 00FE, it executed the 2-byte instruction LDH-FA. The moment the internal hardware saw that write, it disconnected the boot ROM from the bus, routing the lower address line straight to the cartridge pins. Because that instruction ended at address 00FF, the processor's program counter simply rolled over to address 0100 and started running the game without needing an explicit jump. Once register FF50 was written, software couldn't turn the boot ROM back on. It vanished from the memory map until you turned the power switch off and on again. Because the bootloader vanished instantly, early emulator authors in the 90s couldn't read the code. Emulators had to fake the post-boot state and skip the startup sequence entirely, because nobody had an actual binary dump of the original 1989 silicon. Getting those 256 bytes took an optical autopsy. In July 2003, 14 years after the Game Boy launched, hardware researcher Neviksti found a way in. He used acid to chemically remove the chip's epoxy packaging, exposing the bare silicon underneath. Working under a high-power microscope, he photographed the physical layout of the mask ROM array and read the individual bits by hand, transcribing all 2,048 bits of the original program. Years later, researchers like Kostas Sideris used clock glitching on devices like the Super Game Boy to dump later bootloader revisions electrically. But it was Neviksti's microscope work that gave the world its first look at Nintendo's original code. Long before researchers decapped the processor, unlicensed developers found a hole in how the bootloader was designed. In modern security terms, it was a classic double-read flaw, what engineers call a time-of-check to time-of-use vulnerability. The Game Boy read the logo data from the cartridge at two completely different times. First to draw the image on the screen, and seconds later to authenticate the cartridge. The console simply assumed the cartridge would return the same data both times. Unlicensed engineers realized a cartridge didn't have to be passive storage, it could be an active circuit. The clearest commercial example came from a Taiwanese developer named Thin Chen Enterprise, better known as Sachen. Sachen produced unlicensed Game Boy cartridges and built custom mapper chips, like their MMC-1, to control the bus. Sachen's hardware monitored the console's read activity and changed its address routing between the two logo reads. During the first read, the cartridge could send custom graphics, letting a different logo scroll down the screen. When the bootloader started its second read to run the security check, the cartridge swapped its routing and fed the real Nintendo logo data across the bus to pass the test. By taking advantage of that timing gap, custom hardware could pass the security check without leaving Nintendo's logo on the screen. At the same time, an unauthorized manufacturing scene grew across East Asia. Companies like Bung began selling backup units and flash hardware to developers and hobbyists, while other shops built unlicensed multicarts using cheap programmable ROMs and standard logic chips, copying Nintendo's memory banking on low-cost boards. While Nintendo used this bootloader in handhelds, Sega tried a very similar trademark system on their 16-bit home console. In 1991, Sega released a revised Genesis with the Trademark Security System, or TMSS. The hardware looked for the letters SEGA in the cartridge header. If the code was there, the console showed a screen stating the game was produced by or under license from Sega, and then launched the game. If the code was missing, the system halted. Unlicensed publisher Accolade reverse-engineered the console and added the 4-letter code to their software so their games would work on new Genesis hardware. Sega sued, claiming Accolade committed trademark infringement by forcing the console to display Sega's licensing message. In 1992, the Ninth Circuit Court of Appeals issued its ruling in Sega Enterprises vs. Accolade. The court ruled that when there's no other practical way to make software work on a console, using the code required for compatibility doesn't violate trademark law, even if it triggers a trademark display. Judge Stephen Reinhart wrote that functional requirements for compatibility override trademark exclusivity, and that reverse engineering to understand those interfaces is fair use. The ruling didn't directly decide whether Nintendo's Game Boy check was legal, since Nintendo wasn't part of the case. But it weakened the same basic legal theory across the entire industry. An unlicensed Game Boy developer could now point to a major federal court decision and argue that copying functional authentication data to make hardware work wasn't trademark infringement. Even as the legal landscape shifted, the architecture of that 256-byte bootloader set a pattern Nintendo kept building on for years. When the Game Boy Color launched in 1998, Nintendo expanded the bootloader to a 2-kilobyte program. The Color bootloader handled backward compatibility by checking older game headers. For qualifying monochrome games released by Nintendo, it added up the 16 title bytes and checked an internal lookup table. When two games produced the same checksum, it checked the 4th letter of the title to tell them apart, automatically applying custom color palettes before handing control over to the game. By the time the Game Boy Advance arrived in 2001, Nintendo was running 2 separate boot systems. Native Game Boy Advance games ran under a 16-kilobyte ARM BIOS. That 32-bit BIOS ran its own header checks on a larger 156-byte logo. It also provided built-in software routines for division, coordinate rotation, and decompression that games called during active play. Older Game Boy and Game Boy Color games passed through a separate 2-kilobyte compatibility boot ROM. On later hardware revisions, Nintendo changed how that legacy logo data was handled, finally closing the old double-read loophole. The 256 bytes Nintendo wrote in 1989 didn't create a permanent legal lock, but they proved that real control over hardware doesn't happen in a courtroom. It starts directly inside the silicon.